When we think about calculus, we think about these incredibly powerful rules for things like derivatives and integrals. They just work. But have you ever stopped to wonder where they actually come from? Today, we're diving into the world of classical analysis. We're going to see why our simple intuitions can sometimes lead us astray and how mathematicians had to build a whole new, rigorous framework to truly tame the infinite.
And it all kicks off with a question that sounds, well, almost too simple. What does it really mean for a line on a graph to be continuous, to be unbroken?
I bet if I asked you, you'd say what we were all taught in school, right? It's a line you can draw without lifting your pen from the paper. It feels right, it's easy to picture, and honestly, for most of the functions you run into, it works just fine. But is that definition really strong enough for everything?
Okay, now check this out. This is where that simple idea starts to fall apart. On the left, you've got a nice, gentle curve. No problem. That totally fits our pen-on-paper rule. But look at the beast on the right. That function is actually continuous at every single point, except for at 0. But as it gets closer and closer to 0, it starts oscillating faster and faster, literally an infinite number of times. I mean, just try to imagine drawing that without lifting your pen. No way. This shows us crystal clear that our intuition, as good as it feels, just isn't going to cut it. We need something more powerful.
So, to handle these kinds of weird but totally valid functions, mathematicians in the 19th century realized they couldn't just put a band-aid on the old definitions. Nope, they had to go all the way back to square one. They had to rebuild the entire structure of calculus on a perfectly solid foundation. And you know where that foundation starts? With the numbers themselves.
And this quote from Marsden and Hoffman just nails it. They say that everything, the entire precise treatment of calculus, depends on a deep, thorough knowledge of the real number line. It might sound basic, but this is where the real work begins.
And the secret sauce, the one property that makes it all work, is something called the completeness axiom. In plain English, it just means the real number line has no gaps, no holes. Think about it. The rational numbers, fractions, are actually full of holes. There's no fraction that gives you exactly 2 when you square it. But the real numbers fill in those gaps with numbers like the square root of 2. That property, completeness, is the bedrock for everything else. And here's what that looks like in action. Because of the completeness axiom, we have a guarantee. If you have a set of numbers that's bounded, it doesn't go off to infinity, then there has to be a least upper bound, a smallest possible ceiling for that set. And crucially, that number is guaranteed to exist on the real number line. This means that when a sequence is heading towards a limit, that limit is a real place. It's not going to fall into some imaginary gap.
So, we've got our solid foundation, the number line. What's next? Well, we need a precise way to talk about ideas like getting close to a point. We need a new language, and that new language is called topology. The most fundamental building block in this new language is the idea of an open set. Now, forget the everyday meaning of open. In analysis, an open set is a collection of points where every single point inside has a little bit of breathing room around it that's also completely inside the set. And this is that breathing room we were just talking about. We call it an epsilon disk or a neighborhood. The idea is simple. For any point x, you can always draw a tiny circle around it with some radius we call epsilon. This gives us a formal, rigorous way to talk about all the points that are near x. And here's the kicker. For a set to be officially open, you have to be able to do this for every single point inside. See how you can draw those little disks anywhere in the shaded region? Even for points right up against the edge, you can always just make the circle a little bit smaller so it still fits. That's what makes a set open.
So why do we care about all this? What's the big deal? Because this idea of open sets gives us a rock-solid, unambiguous way to define what it means to be near something. We're finally replacing that fuzzy pen-on-paper intuition with a precise mathematical vocabulary. All right, so now that we've got this powerful new language, it's like we've unlocked a new set of tools. Mathematicians could now create concepts that act like guardrails, helping to describe and control the sometimes wild behavior of functions.
And two of the most important tools in the toolbox are compactness and connectedness. Even before we get into the definitions, just look at these shapes. You can kind of get the vibe, right? The compact sets feel contained, and the connected ones look like they're all in one piece.
So what exactly is a compact set? Well, a set is compact if it's two things. Closed, which means it includes its own boundary, and bounded, which means it doesn't just stretch on forever. Think of it like a perfectly self-contained little universe. And this is a huge deal because continuous functions on compact sets are guaranteed to behave nicely. For example, they're guaranteed to have a maximum and a minimum value. And a connected set, Well, this is it. This is the rigorous grown-up version of our unbroken line idea from the very beginning. Officially, it's a set that you can't split into two separate, non-touching open sets. It's all one piece. And this very idea is the key that unlocks some of the most important theorems in all of calculus.
Okay, so let's recap. We built the foundation with the real numbers. We developed a new language using topology. And we forged new tools like compact and connected sets. Now, it's time for the payoff. It's time to use all this machinery to prove with absolute certainty the things we used to only feel were true.
And really, this is the heart and soul of analysis. It's not always about discovering brand new things. A lot of the time, it's about proving that the things we think are true really are true, and understanding precisely why they're true.
A perfect example of this is the intermediate value theorem. It sounds fancy, but the idea is pretty obvious. It says that if you have a continuous function and you pick any value c that's between where the function starts and where it ends, the function has to hit that value at some point. It can't just magically jump over it.
So why should you care about this theorem? Well, this is the rigorous proof of our pen-on-paper intuition. It's why we know an equation like x cubed equals 5 has to have a solution. It's a foundational idea that's used everywhere, from physics and engineering to finding equilibrium points in economic models. It's a huge deal.
So there you have it. That's the journey. We started with a simple, kind of fuzzy idea of an unbroken line, saw where it broke down, and then watched how mathematicians rebuilt everything from the ground up to arrive at a provable fact with incredible real-world power.
And that kind of leaves us with one last thought. It makes you wonder, doesn't it? What other obvious truths that we take for granted every single day are actually resting on some deep, hidden, rigorous foundation that someone, somewhere, had to painstakingly build piece by piece?